So the name of this talk is ClojureScript, the essence of Alchemy. So I think everybody is well aware JavaScript is quite ubiquitous these days. In fact, if you're trying to write portable code for mobile devices, a lot of companies are opting to do like native shells, but in the app itself, you're actually writing HTML, CSS, and JavaScript. And I think everybody kind of knows. I mean, people really have computers now for the internet. I mean, there are some desktop apps that we use, but the internet is basically the essence of computing. And if you're going to talk about the internet, we're talking about browsers, and the only game in town is JavaScript. So JavaScript, as a lot of people may know, have heard, was invented created in about 10 days, right? So that means in 10 days you don't get to get all the design decisions right that you would like to as a programming language designer. And honestly, JavaScript had very modest goals in the beginning, right? It was actually intended to be used by non-experts to do very simple things. I don't think Brendan Eich ever thought that people would write 20, 30, 40, 50, 100,000 lines of JavaScript, and that would really be the way that people build web apps, like we do today. This is actually an old idea. The essence of this talk is, we have JavaScript, which is has some nice things, but has some things that are not so nice. And so a lot of people said, well, maybe we want to leverage our existing tooling. For example, Google created Google Web Toolkit. What that lets them do is that they have many, many Java engineers, not so many JavaScript engineers. So they can use Java. They can use the same layout tools, whatever they have in Eclipse, and so on. So Google Web Toolkit was kind of this first step to say, well, we can compile Java into JavaScript because the semantics, you can simulate a lot of semantics of Java in JavaScript. Google also has this other new project called Dart, which some of you may have heard of. Dart is particularly interesting because they sort of came out with, it's a custom VM that only runs in Chrome. And they created it in sort of the idea was they were going to move the web forward. Now, the likelihood that any other browser is going to adopt Chrome, adopt the Dart VM is quite small. And in fact, in order for this to really work, they have to be able to compile down to JavaScript. And that actually created some interesting design decisions that they had early on that they had to change, right? By needing to compile down to JavaScript, they had to tweak some of the semantics, specifically because of issues around efficiency. And so this is pretty interesting to me because I think more and more languages will target JavaScript as a compile target, and it's going to be interesting to see what trade-offs you'll have to make in your language. Microsoft jumped into the compile to JavaScript game with Typescript. So Typescript is a superset of JavaScript. So an untyped JavaScript program is completely valid Typescript, but they add sort of class syntax sugar and a fairly sort of straightforward type system. You can gradually type your programs if you like. You can also provide type annotations. Say somebody gives you an untyped library, JavaScript library, you can actually add annotations to the library as a separate file, and that's pretty interesting. Then you have sort of more grassroots projects, compiled to JavaScript projects like CoffeeScript, which is quite popular with young developers. And CoffeeScript is interesting in that it sort of has like Ruby, Python-esque sort of white space sensitive syntax. It sort of has a much more convenient way to write Lambda and so on. But again, it doesn't really try to diverge too far from JavaScript semantics. You have another growing popular compiled JavaScript language called Roy, which sort of tries to bring some of the things from statically typed languages into JavaScript. Again, Roy does try to not veer too far away from JavaScript semantics because, again, he wants to be able to compile, his name's Brian McKenna, he wants to compile readable JavaScript, similar to the strategy that CoffeeScript takes towards the JavaScript that's generated. So all the previous languages I said, they actually sort of, the compromises in the languages are quite large. Again, they're not trying to step too far away from JavaScript. So Clojure is quite different from JavaScript, right? The semantics are actually radically different. It does not try to adopt mainstream programming practice at all. So there are going to be a lot of challenges here in getting something like Clojure to target JavaScript efficiently enough that anybody would want to use it. So I just want to talk about the challenges. First off, if you're going to target JavaScript, whatever language you're going to design, you have to really be serious about the cost-benefit ratio, because what are you imposing on the potential adopter of your language? You're adding a compilation step to whatever they're doing, right? So your language has to provide significantly better semantics, like much, much better, such that the cost of having to go through this whole rigmarole to use your better language is actually worth it. It absolutely needs to interoperate well with the host. Sometimes you see people do these JavaScript languages that try to protect you from things in the DOM and so forth. And I think that's not a great idea. Clojure is an advantage here because Clojure was always designed, even on the JVM, to be a hosted language. Something that's becoming more important is that you really have to have a sensible debugging story. So you have this sort of ad hoc CoffeeScript or Roy approach where you're just generating readable JavaScript. That's one way. But I think it really needs to be better than that. And the story here is improving because Chrome, for example, has source maps, and Firefox has source maps. And that actually allows us to get line and column information for every symbol in your programming language and map them to symbols in the compiled JavaScript. So you'd be able to set breakpoints and step through your code, not the generated JavaScript. Another thing that's big is you need to be able to reach the performance of the host. Whoops. So this one is pretty interesting because I think this may put some restrictions on what you can do. So host limitations, obvious one. JavaScript right now currently is single-threaded. There's not much you can do about that. You can just throw that out the window. A lot of the things that cool things that you're going to hear about here related to concurrency, you can't do in JavaScript. Another big limitation is numerics. So Dart has had to sort of punt on this as well. JavaScript only has 64-bit floats, right? That's all that it has. It's also source only. You often hear people talk about, yeah, wouldn't it be awesome if we could compile down to bytecode? But the reality of having to send things over the network, I mean, it's not going to work. And some language design choices just may be challenging to implement efficiently. Hopefully, what you get from this talk is that I think it's pretty impressive, I think, the sort of collaborative work that's been done on ClojureScript to really get something that really feels like Clojure in the browser. So it's sort of a challenge. Are there other sort of more radical paradigms that are possible to implement efficiently in the browser? Think maybe perhaps languages that emphasize messaging or laziness, like Haskell. So host benefits. The reason you want to do this again is that you have some language that you like, in this case Clojure, and we want to be able to reach all these technologies that JavaScript is capable of reaching, right? It's our only way to get there. Things like HTML Canvas, WebGL, WebAudio, WebRTC, these are all really exciting technologies, and these are things that can run on phones, that can run on browsers, without the user having to install anything. They just have to have the browser. Another thing that's interesting is longevity. JavaScript is a bit odd in that there's now an interest in making it better, but for about 12 years, nothing was going on, right? We're using the same version of JavaScript that we were using in 2000. But that's actually a good thing, right? We have a stable thing to target. The other thing that's nice is that there's also really, unlike a lot of technologies that we use where the sort of floor keeps moving underneath us, vendor competition actually moves towards standardization. So, Apple creates HTML5 Canvas. Firefox adopts it, right? Finally, we have it in IE. But it's a slow process, but we're actually, it's not like the thing where Android versus iOS. It just keeps fragmenting, right? The web is like something where it's moving towards consolidation, not fragmentation. And this is, I think, something that as programmers we like. So this is a real image. I imagine in 4 or 5 years that there'll be many programming languages in the browser. This is like some source mapping work, and I can actually inside Chrome see my original ClojureScript source files, and eventually I'll be able to set breakpoints and step through it. But this is a big step. I would love to see things like perhaps a strict version of Haskell, and you could debug it right there. Like that would be pretty awesome. So I don't think I need to introduce Clojure too much to this audience. It's a dynamically typed Lisp. It did target the JVM, and now it targets JavaScript as well. It was introduced July 21st, 2011. Rich Hickey came out with it then. Since then, its development has really taken off. We have 51 contributors now. There are some contributors in the audience, which is really cool. And so I want to talk a little bit about some of the design decisions about how ClojureScript works in wanting to compile decent JavaScript. So one thing that was controversial early on that I think a lot of people don't really understand is that Google Clojure compiler, which is the optimizing JavaScript compiler, is actually a critical sort of step in the compilation pipeline. And this is a big deal for lots of reasons. One of the biggest is that dead code elimination is extremely good. I'm not aware of any other JS optimizers that do dead code elimination as well as Google Clojure compiler. This is critical for Clojure because Clojure has a very large standard library. It's like 7,000 lines of Clojure that gets compiled into like 20,000 lines of JavaScript. You absolutely need to have extremely good dead code elimination. The other thing is that Clojure is a Lisp, right? So people write macros that generate tons of code, right? You need something like Google Clojure compiler to control that. The other thing that Google Clojure does that's pretty awesome, so that we don't have to write multiple passes for this kind of thing in the actual ClojureScript compiler, is inlining. So for example, JavaScript is a statement-oriented language, right? It's not an expression-oriented language. Lisp is expression-oriented. If you're familiar with Ruby, Ruby is also expression-oriented. It's not statement-oriented. The only way to get sort of expression semantics in JavaScript is to create closures, right? Or to create a function, to wrap the statement. That's the only way for this to work. But that's horrible, right? Because in JavaScript, there's like allocation semantics around writing closures inside your functions. There's a huge performance penalty. Google Clojure will just lift them out. Will lift that statement out intelligently. So we're able to preserve expression semantics without complicating our own optimization passes. Does obvious things like constant folding, and again, minification, which is critical when your target is web browsers and mobile devices. And the other thing that's really nice is that it has a large library of battle-tested JS. I mean, Google probably produces more JavaScript than any other company in the world. So not handled. So when it came out, there were still a bunch of things that we weren't optimizing that Google Clojure can't optimize for us because we have different semantics than JavaScript, right? There are certain things that are Clojure specific that have nothing to do with JavaScript that we need to optimize if we can. And Google Clojure will not do this. These include things like REST arguments. We have multi-arity functions. We have keywords. We often use keywords to extract properties out of associative data structures. Things that Google Clojure, that it's not relevant for JavaScript. We have a type constructor called deftype, right? And when you do it, you actually declare all what are called protocols, and this is actually static information. When you construct a type, there's a bunch of type information there, right? We can actually flow that information through your source and optimize call sites because we have that information available. So these are things that we have to handle. Also things like Boolean inference. So in JavaScript, 0 is false. The empty string is false. So everywhere, because that's not true in Clojure. Clojure, there are only two false values, nil and false. So everywhere that we do a test, we actually have to call out into a function which tests that the value is truthy in Clojure. That's a huge performance hit, especially in any critical path. Imagine having to say 0 is less than 1, and we have to call some other function to guarantee that we're going to get some usable value out of that. So one thing that we added is Boolean inference. So we actually add type hints, which are a part of the way that Clojure works. And in the compiler, we infer that we don't need to do the test. Numerics is something actually we don't address because we still haven't figured out how to do it. We're lucky in that all the JS engines actually, of course, try to hold on to ints as long as they possibly can. Otherwise, the performance would suck. But we can't guarantee, we can't really truly say that we can represent integers in ClojureScript. We sort of just pretend. Very hand-wavy. But it works out performance-wise for us. So I want to talk a bit about, switch gears and talk about data structures. So Clojure is very influenced by this book. I mean, in some sense, there's a sort of meme in the Clojure community called data all the things. I mean, Clojure is really about data and functions. Clojure programmers are dynamic programmers, but pretty much everything else that you'll hear about in this conference, we believe in. We might not care about static typing, but pretty much everything else that you'll hear from a functional programmer, Clojure really truly believes in, and that's data and functions. So when ClojureScript first came out, right, Clojure programmers love the data structures. They're really nice. They provide good performance, and yet they're immutable. And so when it first came out, Rich Hickey only did copy on write, and this was just for expediency reasons, right? He wanted to get something out to the community, and the community could take it over. And there was a lot of skepticism early on, was like, is that even possible? Is it possible to do good persistent data structures if your target is JavaScript? And V8 really changes the game for this kind of type of thing. V8 is very, very, very good. The fragment that's optimizable, V8 does this very well. And really the thing that's killer about V8 is the garbage collector. I mean, it just runs circles around JavaScript Core, which is Apple's product, and SpiderMonkey, which is Mozilla's product. Just to show some benchmarks, so here I have a benchmark where I construct an array with 1 million items in it. I'm just appending them, mutating the array. And then I have a benchmark for doing the immutable construction of a vector. And then I benchmark a sort of a local mutable optimization that Clojure has called transients. You notice we're actually faster. It's faster to build transient vectors in ClojureScript on V8 than it is to build mutable arrays. And that may be because of optimizations that V8 is willing to do, because we actually have we use fixed sizes. We use arrays of 32 elements. And the thing is that that performance is great because really when you're doing browser programming, you're dealing with a DOM, and basically the DOM is I/O, right? If you have to touch the DOM, that's pretty slow. So this is good that we're showing really good performance for these persistent data structures, because we're saying the cost is not high, right? The benefit is high. The semantics of immutable data structures, right? Functional programming, and you're not paying too high of a cost. So I could talk all day, but it's more fun to show some code. So here we are. This is actually running in Chrome. So everything I'm demoing to you is running in Chrome. So this is a very Lispy thing to do. We actually use the browser as an evaluation environment, right? So we actually compile the JavaScript on the fly. We send it to the browser. It evaluates, and we show the result back out in the REPL here. So I'm actually compiling this on the fly, evaluating in Chrome, and getting the result back. Already you see we can do things that you can't do. We have some notion of modules, right? Clojure has namespaces, and that's pretty awesome. So I'm just going to show some basic things like, false is false, sure. Nil is false, okay. 0 is not false. The empty string is not false. A small victory, but a nice one. Another one that this is big, which is that JavaScript has no sensible notion of scope. It's bad. It's horrible. So I just want to show you that we actually have the semantics of lexical scoping. So here I'm going to make an atom. It's the mutable reference type in Clojure. I'm going to have a for loop here where I create closures, and I stick the the current value of the iterator variable inside, right? So I'm just going to side effect that thing. In JavaScript, if we actually mapped over it and force those thunks, we would get 4, 4, 4, 4, 4, 4, right? This is what you want to see. This actually burns nearly anybody that does any JavaScript programming, because it's very normal to have a for loop, construct some AJAX callbacks or what have you, and then you run it, and then suddenly none of the values make any sense. So the compiler intelligently closes over any locals that we need to. This is also another small victory, but I think pretty significant. So again, data all the things. If you saw the talk this morning, sort of having something like type classes is pretty sweet. So Clojure doesn't have precisely type classes, but does have something called protocols, and allows us to do the kind of generic programming that was demonstrated this morning. So for example, I can get the first thing in a list, I can get the first thing in a vector, I can get the first thing in a set, I can get the first key value pair in a hash map, and I can get the first character in a string. So generic programming. We have a large set of data types, and we have a uniform way with working with all of them. I can loop over the contents of a vector, and I can print them all out in the same way that I can loop over the contents of a hash map and print them all out as well. Hopefully you can see that. OK. So the other thing we have, and this, Ben Mosley, I think I talked about this, but we have sensible notion of equality, right? So in JavaScript, you really have nobody uses the equals operator unless you're just checking for identity. And in Clojure, we don't do that. We want to know that we program with values, and it's very useful to compare two values. And we don't care that whether these things are the same in memory. We care, do they represent the same value? And we can do that sensibly, and it's just built in. Here's comparing two hash maps, and yes, they're equal. Something that's kind of fun that you probably won't see in a language at least like Haskell, is that collections in Clojure are functions themselves. So for example, I can create this data structure which represents some address, right? And I can actually use that data structure as a function, right? Hash maps in Clojure are functions of their keys. So I can take a sequence of keys and extract out a sequence from the address, right? So I want to get the city and the zip, and you can see I have them right there. I just want the city, or I want the zip first, right? And so on. Another thing that's nice is Clojure doesn't have pattern matching, but it does have ubiquitous destructuring. So destructuring is a way to take some data structure and extract out some value that you actually care about. So here I say, give me the middle element of that vector. But it's recursive. I can do this as much as I want. I can extract out the first character in the middle value. We can go even further. There can be a hash map there. I can destructure the hash map and extract the first letter for that particular key. And this is pretty great, right? So again, this is sort of showing that this is very different from what JavaScript programmers do, which is sort of create some mangled monstrosity, right? This is emphasizing programming with data. Clojure has a lot of nice features for dealing with data. A little thing, so this was a bit challenging to get right. Multi-arity fns. So here we have a regular function which will compile down to a regular JavaScript function. But we have to do something special in this case, right? We want to dispatch based on how many arguments you get. And JavaScript does actually provide a reified arguments object, right, where you can actually inspect which arguments were passed to the function. But there's a performance cost associated with that. And we don't want to pay for that because multi-arity functions pervade the Clojure's standard library. So here's a little hack. I want to be able to call the compiled function. And let's see, that takes 163 milliseconds. And this is the multi-arity dispatch. So this is showing that I can call a particular arity of that function faster than I can even call a regular JavaScript function. And this is probably because various tricks that the Google Clojure compiler does with this code. OK, so it's a little bit of live coding. So one thing that I want to talk about is that there's a whole sort of process. We're trying to transform Clojure into JavaScript. But once we get Clojure into the browser, we really can do something great for the user, which is the user is also able to transform the browser into a more ideal programming environment. So here you see I can grab the div on the page. I can make it blue, make it big, make it small. I can apply a CSS web transition. Where this gets really fun, and that's not that exciting. We're just mutating the DOM, whatever. And it seems a little bit more verbose than what you would do in JavaScript. But what if we decide, I actually want all HTML nodes in the browser to be safely extended to be functions. I want them to be functions. I want them to be functions of their attributes in the same way that hash maps are functions of their keys. So I've just extended HTML elements so that now HTML elements are functions. I can map that HTML element over a sequence of strings and extract the ID and the class, right? So this is great. Like now the programmer can transform the browser environment to be something that's more malleable and more fun to work with. We can also do that. There's another protocol, which again, it's a bit like Java interfaces, but really more like Haskell type classes, called iLookup, which is the associative protocol. And so now I can actually take that same HTML element and I can destructure its key, right? So I can extract the class and I can get the first character off the class, which was spin. Spin was the CSS class that I added to make it spin. So, and if anybody has questions, you can stop. Sorry, I didn't say that earlier. If somebody has questions, you raise your hand and I'll address them. So let's get back to the slides. OK, so let's talk about, now that we have something that looks basically like full-blown Clojure in the browser, what are the fun things that we can do? So Clojure doesn't ship with pattern matching, but we can add it because we have macros. So something I did actually a year ago was I read a really great paper by Luc Moranger, who is a OCaml person. And he's written some really great papers on writing optimizing pattern match compilers. And I read it, and the paper's great. And it's easy to read because he doesn't talk too much about the types. He just talks about the algorithm. And the algorithm is really great. It sort of takes the semantics of lazy pattern matching and shows you how you can make an algorithm that can simulate that. And what's cool about the semantics of lazy pattern matching is that it produces really nice trees. Whereas you see that there are many paths to match a certain pattern if you do a naive pattern match compilation. Doing it with their algorithm produces a single path. Right? It's the same match, but there's only one way to get there, and it's pretty short, only 4 steps. So I and this fellow Ambrose Sargent, last summer we worked on this, and this is also pretty fun. So I don't know if you all are familiar with red-black tree pattern matching, but this is the red-black tree pattern match, which actually was broken for a long time. Tom Christensen is in the audience, and he helped me debug this. So this is exactly like what it would look like in Haskell, right? Except, right? It's like we're able to write the pattern very succinctly. And so I'm going to, is this balanced? And it's not. And I get it back a balanced node. This one is, and we get back the node that we gave it. And how fast is this? So this is, we put a lot of work into efficiency. So this is not the fastest way to do this. We could write custom red nodes and black nodes. I want to show that the persistent vector performance is pretty good, and the pattern match performance is pretty good. So we were able to call that 500,000 times. That's not bad, 1 second. So one other thing I want to show is logic programming. So I invite you to come to my talk tomorrow. I will talk significantly more about logic programming. It's a passion of mine. How many people know Prolog here in this audience? This is great. You know you're at TechMesh when this many people raise their hand. So if you know Prolog, Prolog is really great for solving puzzles. No, it's actually good for a lot of things, but it's good to demonstrate its power with a simple puzzle. And a famous one is the zebra puzzle. It appeared for the first time December 17, 1962, and it looked something like this. It said, "Who owns the zebra?" And there are 15 sentences, and they all are about 5 properties of 5 houses. And the properties are who lives, what's the nationality of the person that lives there, what do they like to smoke, what type of animal do they have, what do they like to drink, and what's the color of their house. And so it goes, there are 5 houses, the Englishman lives in the red house, the Spaniard owns the dog, coffee is drunk in the greenhouse, and so on. And it ends with who drinks water and who owns the zebra, right? In this great book, Peter Norvig, The Paradigms of Artificial Intelligence, Peter Norvig actually shows you how to write Prolog, an interpreted Prolog in Common Lisp. Then he shows you how to write a compiled Prolog in Common Lisp. And he points out that the naive, like brute force search of this space involves about 24 billion candidates. And he shows that once you've got this really nice compiled Prolog in Common Lisp, he was able to solve it on decent hardware in 1993 in about 17 seconds. So I'm going to show you how fast we can solve it using V8. So, oops. Actually, so that benchmark is for calling zebra 100 times. So we can solve it in 14 milliseconds, which is pretty cool, right? This is something you can run in your browser. Like we should be thinking very differently about the types of programs we can construct, given that we can write in higher level languages, and we have, our computers are just so fast now. I mean, I think we still tend to think in a very old-fashioned way about the types of programs we can write. So here we find out that the Norwegian must drink water because the middle property is the drink, and the Japanese man owns the zebra. So if you're interested in this, again, come to my talk tomorrow. I'm going to talk a lot more about logic programming. I sort of implemented a version of a system called Mini Canron that's described in the Reason Schemer. If you've heard of the Little Schemer, Dan Friedman worked on the Little Schemer. If you're familiar with Haskell, I'm sure you know who Oleg Kiselyev is. This book is really amazing. I love it. It's really cool. It basically shows you how to embed Prolog, something very similar to Prolog, in about 200 lines of scheme, which is pretty incredible. That's really tiny. So types. So I'm going to so Ambrose, who I collaborated with on the pattern matching stuff, he actually works on a thing now called typed closure, which is sort of taking some of these great ideas from typed racket to add types to Clojure, to actually type Clojure. So I don't have a totally cool demo, but this is still pretty interesting. So what this does is that here he's given this function a type, right? He's saying that we're going to union nil, and it's going to return some value, Boolean CLJS, say CAJS. And so what's cool about this, right, is that he had to modify his type checker only slightly, right? Only a tiny change had to be made to his type checker to check ClojureScript, because ClojureScript is not a dialect, right? ClojureScript is so close to being Clojure that just happens to run on JavaScript. So I believe yes. So if you run this code, we see that the type checker runs on that namespace in ClojureScript, and it emits a bunch of type information that was collected during the type checking process. So anyways, hopefully you enjoyed this presentation and convinced that JavaScript is actually a pretty awesome target for much better languages than JavaScript. Right? I think you can write really great languages, and JavaScript can be a really good target. The thing that I'm fascinated by, and this whole enterprise has gotten me excited about, is that we need to explore efficient implementations of different paradigms that target JavaScript, so that we can find sort of new implementation strategies, right? A lot of this just requires people to say, I wonder if I can get laziness to be fast on JavaScript. You see people often do this naive thing where you have hundreds and hundreds of thunks, and it just doesn't work, right? People have to, if they're going to try to do that, they have to come up with new ways of implementing that particular approach to programming language design. The other thing is JavaScript is not likely to go anywhere. It's not going to go anywhere. And we have to ask ourselves, do we still want to be programming in JavaScript 10 years from now, 20 years from now? That's all I had. Questions?